Hello, this is Murki Devi. Thank you for listening to my talk on pinpointing octant of the atmospheric mixing angle θ23 for a linear seesaw model under A4 symmetry. I would also like to thank the organizers and PANIC committee members for giving me this opportunity to present our work in this conference. This work is done under the supervision of my research guide, Professor Kalpana Bora from Department of Physics, Guwahati University. So we already know that neutrino is an elusive particle which has been proved to be massive. Eventually, the neutrino oscillation parameters have been measured with unprecedented accuracy by neutrino oscillation experiments such as Diabe, Double Choose, Reno, and T2K. Neutrino mixing gives us a strong evidence of beyond the standard model physics. One of the popular mechanisms to generate the tiny mass of neutrino is seesaw mechanism. Although the neutrino oscillation parameters have been measured to a great extent, there are still some unknown neutrino oscillation parameters and open issues related to the neutrinos, such as what is the mass hierarchy of the neutrino, the absolute masses of the neutrino, and the octant of the atmospheric mixing angles, which are still yet to be answered. In order to resolve these issues, we have constructed a linear seesaw model by incorporating an A4 flavor symmetry along with other symmetries such as Z4 and Z5. One of the main advantages of using the linear seesaw model is that it's a low-scale seesaw model, hence it is testable in ongoing and future neutrino experiments. So the question is, what is A4 symmetry? A4 symmetry is a group of even permutations which includes 3 singlets and 1 triplet. These are the basic tensor product of A4 symmetry that we need to follow while constructing the Lagrangian of the linear seesaw model. By applying the product rules of A4 symmetry, we obtain the Lagrangian of the model. The lightest neutrino mass matrix can be obtained by the relation given in the third bullet, which ultimately gives us the light neutrino mass matrix of the form as given in equation 1. We also know that the light neutrino mass matrix can be evaluated as shown in equation 2. Thus, by comparing equation 1 and equation 2, we get a set of simultaneous equations which can be solved to find the unknown neutrino oscillation parameters such as the lightest neutrino mass, the delta CPV phase, and the 2 Majorana phases. This is done for different wave alignments of the triplet flavon fields. We use the global fit values of neutrino oscillation parameters as input in order to solve the simultaneous set of equations to evaluate the unknown neutrino oscillation parameters. So we solve the set of simultaneous equations for 26 cases of the wave alignments of the triplet flavon field, out of which we get 6 allowed wave alignments. We choose only the very accurate solutions of the set of equations for which the tolerance is less than or equal to 10 to the power minus 6. So from table 2 we see that we get 6 allowed cases, out of which in case A we have 0, -1, and 0, 1 wave alignment of the triplet flavon field, which is allowed only for the normal hierarchy. Similarly, in case B is allowed only for the normal hierarchy and the wave alignment is 1, -1, and -1, 1. As well as in case C, we see that for the wave alignment 0, -1, 1 and 0, 1, -1, it is allowed only in the case of the inverted hierarchy. So it is clearly seen from table 2 that the favored octant for case A is lower octant. We can find that from the range for atmospheric mixing angle θ23. Similarly, the favored octant is the higher octant for case B, and the favored octant is the lowered octant for case C. Thus, to summarize, from our model, we are not only able to compute the unknown neutrino oscillation parameters, that is the lightest neutrino mass, delta CPV phase, and the Majorana phases, but also we are able to pinpoint the mass hierarchy and the favored octant of the atmospheric mixing angle θ23 for specific wave alignment of the triplet flavon field. This result can be seen to have profound physical implications on the internal symmetries affecting the mixing between the second and third generation neutrinos. And this model can be tested soon by neutrino experiments, so stay tuned for the more progress in our work. I would also like to thank our HOD, my PhD guide, my friends and family for supporting me throughout this work. I sincerely thank Dr. Debashish Bora of IIT Guwahati for his fruitful discussion, suggestion throughout all the stages of this work. So that's all. Thank you for having me.